Antiderivatives and indefinite integration. So we know by now how to differentiate functions. We're gonna learn how to reverse the effect of differentiation. That process is referred to as anti-differentiating. Let's put some terminology in place. A differentiable function capital F is said to be an antiderivative or primitive function or indefinite integral of a function little f. So capital F is said to be a primitive function of little f on an interval I, provided the derivative of that capital F is equal to little f on I, on the interval I. Okay. So the problem, the anti-differentiation problem is to find a function, in this case labeled as capital F, whose derivative is that known function little f on some interval I. Okay. If that function capital F exists, it's referred to as an antiderivative, primitive function, or indefinite integral of that function f on that interval I. So for instance, if we take the function, little f to be the squaring function, so x squared, and let's take the interval I to be all of R, all of the set of all real numbers. It's not hard to discover an antiderivative of little f, okay? Just keep the power rule in mind, and you're gonna quickly realize that an antiderivative would be x cubed over 3, right? Correct? Check. If you differentiate, certainly this is a differentiable function, right? This capital F is a differentiable function on all of R. It's a polynomial. And the derivative of capital F is certainly little f, right? Differentiate this. Isn't it 3x divided by, 3x squared divided by 3, so x squared. So we get this. So certainly this identity here holds for all of x. Okay, so capital F is an antiderivative, or a primitive function, is a primitive function, FCT for function, of little f, right? Agree with me? All right. However, if you take g of x to be x cubed over 3 plus 1, this is also a primitive of little f. Why? Because this function is certainly differentiable, right? And the derivative of capital G is equal to little f, right? If you differentiate this function, it's the same as differentiating capital F plus 0, right? Plus 1 prime, the derivative of 1 with respect to x is 0, right? So this is also a primitive function of f. All right? And I hope now you understand why here we said in the definition, why we said an antiderivative. Because, an antiderivative, when it exists, is not unique. Okay? It's not unique. Look, I have 2 here. And in fact, you have infinitely many. Whatever constant you throw in instead of 1 is going to do the job as well, right? So let's record this. Whatever constant, as we said, you replace 1 with, that's gonna also do the job. So even that thing, let's call the constant c, where c is an arbitrary number in R. So where c is an arbitrary constant, arbitrary real number, that's also a primitive function of f on all of R, right? So of f. Do you agree with me? So h of x equals x cubed over 3 plus any constant. So you have infinitely many choices for the constant. As such, you have infinitely many antiderivatives or infinitely many primitive functions of little f, right? And hence this article is an indefinite article because of the non-uniqueness of that antiderivative. Okay. All right. The question then becomes, are these all of them? Is this family? This is a family of antiderivatives, right? For each constant, you have one antiderivative, and if you let c varies inside the real set, the set of real numbers, you're gonna pick up a family of primitives, right? So the question becomes, are these all of them, or are we missing some others with which we haven't, or which this function doesn't dictate? So let me write the question. The question now is, is um, is any antiderivative of little f given, is it given by the recipe h? What's h? This one, right? Is it given by this recipe? So in other words, are these all of them? Are these all the primitive functions of little f? Well, let me take you back to an earlier section. Let's recall that thing. Do you remember the following? Definitely, we didn't have the same labels, but look, if we have t prime equals s prime on some interval, so if you have two functions so that their derivatives are identical on some interval, what did we show at the time using the mean value theorem? Remember, we used the mean value theorem at the time. What did we show? We showed that t is equal to s plus some constant. Correct? Do you agree with me? So that thing was was proved, or at least discussed in an earlier section, and it uses the mean value theorem, and it says if two functions have identical derivatives on an interval, then they must differ by a constant. Meaning t minus s is equal to a constant. So take it back here. If you have two antiderivative of little f, let's call them t and s, then certainly t prime is s prime, right? Because t prime is f if t is an antiderivative. Remember this? If t is an antiderivative, so t prime is going to be little f. And if s is an antiderivative, then s prime is going to be little f. So we get that t prime and s prime are the same on that interval, that the underlying interval. And as such, they must differ by a constant, which means one is equal the other plus some constant. So that tells us that h is the recipe of, or any antiderivative is part of this family, right? So long story short, to answer this question, yes, this is any antiderivative of f is given by this recipe h. Okay, because of that trick that we did before. Makes sense? Pictorially, how does this look? How does this look? I mean, what does it mean that t and s differ by constant? This means that t, I don't know, some function t, I have no idea how it looks, and s, they differ by constant, which means that they are identical up to a shift, right? So if you take this, you copy it, and you paste it, right? And you paste it. So they are the same, but via a shift. Okay? So let's color this, let's say, in, I don't know, green. And then if one of them is t, the other is s, let's say that this is t and this is s, and that shift is that constant c, right? That vertical shift is the constant c. So what does it mean? Well, graphically it means that we're gonna obtain a family of functions whose graph, because of this, a family of functions whose graphs are vertical shifts of one another. And this makes sense because each curve I mean, they're technically the same curves, but shifted. Each curve must have the same slope at any given value of x. So they must have the same slope, right? The derivative of any of these two functions is going to be the same as little f in this case, right? So the derivative of t and the derivative of s are going to be the same, and hence they're going to be the primitive functions for the same function little f in some sense. Correct? All right, so because of this discussion, what can we say? What can we say? That once you have an antiderivative, you add a constant, an arbitrary constant to it, you covered all of the family of antiderivative of a given function little f. Correct? So once you find one primitive function, you add to that function a constant, arbitrary constant c, and you discovered all the primitive functions of that function little f. All right? So this is the takeaway from the discussion here. And hence we have the following theorem. If capital F is an antiderivative of f on an interval I, then the most general antiderivative of f on I is that function capital F plus a constant where this constant is arbitrary in R. Okay? All right. So that thing we're gonna have a notation for this because of the theorem we just mentioned above. The most general antiderivative of little f on an interval is denoted by that symbol. Okay, what is that symbol? This is the symbol of the most general antiderivative of little f. You see little f here? Okay, and dx is because we are because of this, right? Because we are differentiating. Remember, this prime is the operator d over dx, right? This is the operator d over dx. We are differentiating with respect to x. So that operator somehow is going to have an interpretation in the notation, right? Because it's an active ingredient in that process. All right, so and hence this dx thing. So again, what is this picture? This picture means the most general antiderivative of f. All right. Okay, so this means if you want to sum it up, you get this. That symbol is by definition equal to capital F of x plus c, where f prime, where this guy, if you differentiate it, you get back this piece f of x. So where this guy, capital F, is an antiderivative of little f, meaning f prime of x is equal to f of x on that the underlying interval, right? And c is an arbitrary real number. All right? Okay. So every differentiation rule is gonna give us a rule for anti-differentiating. For example, if n is a real number, then the primitive of the function n, this is a constant, the primitive of that constant, I mean, what's a primitive function of that constant n? Give me a function so that if you differentiate it, you pick up n. Well, nx is something like this, right? And once you find one, you add an arbitrary constant. That sum is the most general antiderivative of that function n, right? So based on the notation above, that thing is that guy, where c is an arbitrary real number. Make sense? To check again, what do you do? Try to differentiate this thing. If you differentiate this thing, you should get n, right? Differentiate that. Well, the derivative of nx with respect to x is n, plus the derivative of a constant is 0. So this whole thing, if you differentiate it, you get back n. All right? Makes sense? Part 2, if you differentiate xn, again, what's n here? It's still a real number. If you differentiate that, as long as n is not negative 1, then what you get is x to power n plus 1 over n plus 1 plus a constant, and that constant is arbitrary. If you don't believe me, let's try it backwards. If you differentiate that thing, you're gonna get n plus 1 times x, right? How about we try it together? If you try to differentiate with respect to x that thing, xn plus 1 over n plus 1, if you differentiate, what do you get? You get n plus 1 times x to power n plus 1 minus 1, correct? Divided by n plus 1. Now what is that? N plus 1 and n plus 1 cancel each other. The 1 and negative 1 cancel each other. What do you get back? Xn, right? You get back that. So this is n antiderivative, and if you add a constant to it, you got the most general one. Okay, so you get that. Hope it makes sense. All right, let's erase all of these. All right, moving on, part 3. The primitive function of cosine x is sine x plus an arbitrary constant. Why? Because if you differentiate sine, you get cosine. And then to find the most general one, you add a constant to it, arbitrary constant. Primitive function of sine is cosine of x, correct? As negative cosine of x, I mean. Why? Because if you differentiate negative cosine, what's the derivative of negative cosine? It's the negative of the derivative of cosine, which is negative sine. Negative, the negative becomes plus and sine, right? And then to get the most general one, you add a constant. And so on, right? These formulas are just writing the differentiation formula, but in some sense backwards. That's it. Okay, so this list of properties is can be shown immediately, right? And it's just the backward direction of reading it for differentiation. All right, primitive of sec squared. What's a function if you differentiate, you get sec squared? Well, if you take one moment to think about this, this is tangent. And if you add an arbitrary constant, you pick up the most general antiderivative of secant squared. All right, primitive of sec tan. What's a function that once you differentiate it, you get sec x tan x? This is a product here. Well, that's secant. Add a constant, you pick up all of them, or the most general one. Primitive of cosecant squared is negative cotangent of x plus an arbitrary constant. And lastly, the primitive of cosecant times cotangent is negative cosecant of x plus a constant for the same reason. If you differentiate this side, you're going to pick up this side. Okay, all right, let's start by doing some problems. Let me start with primitive of 4 dx. Primitive of 4 dx, well, 4 is a pure constant. 4 is a pure constant. And if you take a look at the first property here, you see this first property? Who's n in my context? That's going to be 4. Primitive of 4 dx is going to be 4x plus a constant. And that constant is arbitrary. Correct? So this is simply by property 1. This is simply by property 1 with n equals 4. N equals 4 in that property. That's going to give me 4x plus c, where c is an arbitrary number, is an arbitrary constant. And by constant, I mean a number in R, right? In R. Okay. Makes sense for the first? The second one, primitive of x to power 1/3 dx. Well, this is of the form xn, where n is not negative 1. Where n is not negative 1. By the way, I hope you understand why n is not negative 1, because if n is negative 1, this doesn't make sense, right? So the formula doesn't apply in some sense, and hence we gotta do something else. We'll learn this in future sections. All right, so what we have below is of the form primitive of xn, and in this context is 1/3. Correct? What do we get? This is x to power 1/3 plus 1 divided by 1/3 plus 1 plus an arbitrary constant. So here I get primitive of that is x to power 1/3 plus 1 divided by 1/3 plus 1 plus an arbitrary constant. All right, now let's, if you want to clean up this sum, what's 1/3 plus 1? What's 1/3 plus 1? Isn't it 4/3? Right? 1/3 plus 1, if you do the same denominator, this is 1 plus 3 over 3, so 4 over 3, divided by the same guy, 4 over 3, plus an arbitrary constant. Agree with that? All right, and dividing something by 4/3 is the same as multiplying by the reciprocal of 4/3. One more time. We are dividing this guy by 4/3. And if you are dividing by 4/3, that's the same as multiplying by 3/4, the reciprocal of 4/3. X to the power 4/3 plus a constant, right? Obviously, C is an arbitrary real number. Make sense? This is, I mean, C is called, since here we are talking about indefinite integral, as the definition above says, this is an indefinite integral. Does it say that? Yeah, indefinite integral, right? So that constant C is said to be a constant of integration. Okay, so it has this this name attached to it. It's a constant of integration. So integrating is in some sense reversing the effect of differentiating. Okay. All right, this one, primitive of 1 over x to the power 5 dx. Well, we don't have a formula for this, except once you realize that this guy can be written as x to the power -5, right? That can be written as x to the power -5. Remember, negative in the exponent means the reciprocal of the thing, right? This is the reciprocal of x to the power 5, which means that. Okay. By the way, the guy that sits here is called the integrand. It's called the integrand. That's terminology. Okay. And what is that? This is now of the form. This is now of the form like this, right? Where n is -5. Certainly is not -1. So still using part 2, we're gonna get x to the power -5 plus 1 divided by -5 plus 1. Okay, by property 2. I forgot to label at the time here that this is by property 2. And now I'm gonna have also here by property 2 the same thing. Oh, sorry, not this one, my bad. The next one over here, that's gonna be x to the power n plus 1 over n plus 1 plus an arbitrary constant. All right, and what is this? X to the power -5 plus 4. -5 plus 1, sorry. -5 plus 1 is -4, divided by -4 plus c. Okay, now what is that? Another way to write it is -1 over 4x to the power 4 plus c. Correct? Why? Because x to the power -4 is 1 over x to the power 4. X to the power -4 is 1 over x to the power 4. All right. Next, primitive of the third root of x squared. All right, what is that? This looks very strange integrand. Not once you realize that this can be written as x to the power 2 over 3. Right? Taking the third root of x squared is the same thing as raising x to the power 2/3. This is a notation, right, for this. Correct? And now property 2 kicks in again. This is of the form primitive of xn. So property 2 kicks in, and we get, property 2 kicks in. So now we integrated. We don't need that integral, this integral symbol anymore. We don't need that thing. Now we've integrated, so we get x to the power 2 over 3 plus 1 divided by 2 over 3 plus 1 plus an arbitrary real number, constant c. Make sense? All right, and now let's uh, make this look better. I mean, aesthetic, algebraic things here. What is that? What's 2/3 plus 1? 2/3 plus 1 is 5 over 3, correct? If you do the same denominator, this is 3 over 3. 2 plus 3 is 5 over 3. Okay, and downstairs as well. Plus that arbitrary constant c. And now dividing by 5/3, as we said above, dividing by 5/3 amounts to multiplying by the reciprocal of that, which means multiplying by 3 over 5. Yes? Plus c, where this c is an arbitrary real number. Sounds good? Always, if you want to make sure that your work is correct, how about differentiating this result? You should get back this piece. How about you try it just orally? If you differentiate this one, well, the constant, if you differentiate that constant, it's gone, it's 0. If you differentiate this one, is the same as differentiating that piece, which means you'd bring down the 5 over 3, and 3 over 5 times 5 over 3 is 1. We're done with the coefficient. X to power 5 over 3 minus 1. And 5 over 3 minus 1, because 5 over 3 is 2 over 3 plus 1, right? If you lose 1 from that, you're losing this one technically. So we get just the 2/3. And we get back that one, because x 2/3 is that guy, right? Okay. All right. Next, properties that also have to do with formula or rules for differentiation, right? Remember, if you differentiate a constant times a function, you can push out this constant, right? So the operator d over dx is linear. Is linear in the sense that you can push out constants and it splits, it commutes with addition. Okay, and because of that, it has to also do with it has to commute also with subtraction at the time, right? So since the operator d over dx is linear, it allows us to push out constants, multiplicative constants, I should say, and because it allows us to split some, integration is going to behave the same way because it's the reverse of that process. Okay, so long story short, we have the following two properties. Primitive of a constant, a multiplicative constant, times a function. If this is your integrand, that's the same as pushing that n outside. As pushing this n outside. Oops. So you get n times the primitive of f of x. So it suffices to find an antiderivative of f and then multiply it by n. You give yourself the n antiderivative of n times f of x. Okay? So if you want to find an antiderivative of a constant times a function, it suffices to find an antiderivative of the function and then multiply that antiderivative by n. Similarly, if you want to find a primitive or an antiderivative of a sum, find the primitive or a primitive function for each one and add them up. And likewise for differences. Okay, if you want to find the primitive of a difference, then find the primitive of each and subtract the results while obeying the order that existed already, right? So the g comes next, right? You're subtracting the g derivative, primitive, from the primitive of f. All right, here's an example that puts these two in action. Find all functions g such that their derivative is equal to 4 sine x plus this quotient, 2x5 minus square root of x divided by x. By the way, a function like an equation like this is called differential equation. So what's a differential equation? A differential equation is an equation that involve the derivative of a function or the derivatives of a function. In this case, I have first derivative. It can involve higher order derivatives of that function g. Okay, so this is called a differential equation. Okay, how about I actually write that? This is a differential equation. Okay. All right, so how can we find all these functions g? So I want to find g so that if you differentiate g, you get 4 sine x plus la la la, right? So we're going to find all primitive functions of this guy, right? So we want to label it as g. We want to find all primitive functions of the sum, correct? All right, how about we rewrite this in a slightly different form so we kind of set the stage to integrate. This is the same as 4 sine x plus 2x5 divided by x minus square root of x divided by x. Am I correct? Imagine you want to go back, you just have the same denominator and then you can glue them together. You get back this, right? I'm splitting that quotient. So we get 4 sine x plus, what's x5 divided by x? You get x to power 5 minus 1. And what's 5 minus 1? It's 4. Minus x to power half above, right? I mean upstairs. This guy is x to power half. And what's x to power half divided by x? It's x to power half minus this one here, right? Minus, how many copies of x do you have downstairs? It's just one copy, right? So what's x to power half minus 1? What's x to power half minus 1? You get, oops, this is a different color. Just a second. How about this? X to power half minus 1. And what's half minus 1? It's negative half, right? So it's negative half. So we get this. All right. Okay, so this is the function g prime. I would like to find all primitive functions whose derivative, or all primitive functions of this guy, which means I would like to find little g so that, all little g, so that if you differentiate little g, you get this. Well, g of x is, since g is a primitive function of g prime, so I have this, right? So I have this. Agree with me? So g of x is a primitive of g prime. Okay, plus a constant technically, right? Plus a constant. All right, and then this is what? And then this is what? This is the primitive of this whole thing, correct? So this is the primitive of this whole thing. Makes sense? Because g prime is this guy, right? All right, and now how about we use these two properties? What do they say? They say you can push out multiplicative constants outside the integral. You can push them out as long as they are multiplicative constants. And you can split sum and differences, right? All right, so you see here I have a sum, I have a difference. Let's split them up. So this becomes the primitive of 4 sine x dx plus the primitive of 2x4 dx minus the primitive of x to power negative half dx. And this is by what? Which property did I use here? This is by 2 above, right? By 2. So this is by 2. Makes sense? All right. And now do you see that this is a multiplicative constant? So I can push it outside. Do you see that this 2 is a multiplicative constant? By property 1, I can also push it outside. Now what do we get? We get that this is the same as 4 times the primitive of sine x dx plus 2 times the primitive of x to power 4 dx minus the primitive of x to power negative half dx. Correct? So that g that I'm looking for is like this, right? Okay, what's the primitive of sine? What's the primitive of sine? What's the function so that you differentiate it, you get sine? It's negative cosine. It's by property 4 above, right? If you differentiate negative cosine, you get sine. So what's the primitive of sine? Is negative cosine. Okay. So back here, negative cosine. So this becomes 4 times the primitive, which is negative cosine of x, plus a constant. This one is going to bring its own constant. How about we call this constant, I don't know, how about c sub 1? Because this guy, primitive of this is technically this. Agree with me? All right, similarly here, plus 2 times the primitive of x to power 4. Let's, again, this is the most general antiderivative of x to power 4. Well, this is of the form primitive of xn dx, and this is the primitive is x to power n plus 1 over n plus 1 plus some other constant. How about c sub 2? Make sense? Minus, same story over here. Same story. X to power negative half, if you integrate that, if you find a primitive for it, that's going to be x to power negative half plus 1 divided by negative half plus 1 plus some constant, again, arbitrary constant. How about C3? Make sense? All right, let's now clean up a little bit the writing. This is negative 4 cosine x plus 4c1 plus what here? This is x to power 5 divided by 5 times 2. So this is 2/5. 2/5 times x to power 5 plus twice c2 minus this minus. What's this guy? Negative 1/2 plus 1. What's negative half plus 1? Isn't it half? So this guy downstairs is the same. This is also half. And if you're dividing by half, this is the same as multiplying by the reciprocal of half, which is 2. Correct? Plus, okay, maybe minus C3. Agree with that? We get this. Okay. So then this is then the same as minus 4 cosine of x. I'm going to keep the constants together at the end. I'll tell you why. Plus 2 over 5 x to power 5 minus 2x to power half. These are all the terms in terms of x. And then I'm going to have the constants. So plus 4c1 plus 2c2 minus c3. Am I correct? And what is this? What is that thing equal to? It was equal to gx plus c. It was equal to gx plus c. Let me erase this to make some room. Okay. So this is equal to, one more second. So this is gx plus c that equals that, right? And remind me what c, c1, c2, c3 are. They were arbitrary constants, correct? Remember, see how we picked it up? We were looking for the primitive of the g prime, and that thing is the most general antiderivative of g prime, right? This is what the symbol is. We know g is one guy, If you add a constant to it, you get the most general one, right? This is what we discussed above. So C is an arbitrary constant. Similarly, C1 and C2 and C3, these are constant of integration, right? So what do we get? We get that gx, let's subtract C from both sides. We get that gx is equal to minus 4 cosine x plus 2 over 5 x to power 5 minus 2x to power half plus 4c1 plus 2c2 minus c3 minus c. Remember, I was subtracting by c from both sides? We get this. And as we said, c, c1, c2, and c3 are arbitrary constants. So these are definitely an arbitrary constants. So what can you say about their sum then? What can you say about this whole package? What can you say about this whole package? If each individual one is arbitrary, then this package remains an arbitrary and still a constant, because this is a constant plus another constant minus another constant minus another constant. So this whole package is a constant, and since each one of them, each ingredient inside this package is arbitrary, then the whole package remains an arbitrary thing. So how about we call it, instead of having this ugly notation C1, C2, etc., how about we call this whole package K, a constant K? Okay, how about we call this whole package a constant K? So something like this. The whole thing, I'm gonna call it K. Make sense? So I'm gonna write my final answer, Gx. So Gx, the desired thing, G, is minus 4 cosine x plus 2 over 5 x to power 5 minus 2x to power half plus this package, which I labeled as k because it is an arbitrary thing, where k is an arbitrary constant. Make sense? All right. So this G answers the question. What's the question again? The question is, find all functions g such that g prime is equal to this. These are all of the functions. These are all of the functions. Any function that does this job, any function g, once you differentiate it, you get 4 sine x plus this quotient, is given by this. Okay, is given by this. All right. Next, find f if f prime of x is equal to x square root of x and f prime of 1 is equal to 2. What did we call this at the time? Above, this is an equation involving the first derivative of f, and we refer to it as a differential equation, correct? We refer to it as a differential equation. So this is differential equation, we know that. Okay, remember, a differential equation is an equation that involves the derivatives of a function. And this is certainly involving the first derivative of the function f. Moreover, f prime of 1 should be 2. So this condition is gonna tell us what the constant, remember in the previous problem we had a constant at the end of the day. That guy is gonna tell me exactly what this constant is. As a matter of fact, I think this is f of 1 equals 2. Okay, this is not f prime of 1. This is f of 1 equals 2. Okay, this condition is gonna tell me what the constant of integration is. So I'm gonna have family of functions like I had before. I have family of functions. Remember, for every k I have a function that does the job. And what job I'm talking about? This job, g prime equals 4 sine x plus this, right? So any function that does this job is given by this recipe. So this is a family of solutions to the equation above, right? To the differential equation above. If they give us a specific condition on G, for example, if they told us at the time like G of 1 is equal to 2, they're going to specialize our K. So out of this big family, I'm going to find the individual family that does the job given the condition here. Make sense? So this condition is going to specialize for us the K, the constant. Because if you solve a differential equation, you're going to get a family of functions, and that condition is going to tell us which of these functions belonging to this family is going to be. In other words, what K does the job. This condition is called an initial condition to the differential equation. Okay, this is called initial condition. Right. So this is a condition that's going to reveal to us the member of the family that satisfy the equation, the differential equation, and the initial condition. All right, let's start this one. F prime of x is equal to x square root of x. Same treatment as above. How did we start? We got, in this case, we don't have g, it's f, right? So f of x plus c is equal to primitive of f prime dx. But remember the c at the end of the day, we lumped them up, all the constants, we threw them in one package, the constant package, and we labeled this whole thing as some new letter k. I'm not gonna do it anymore like this, okay? I'm not gonna do it anymore like this. I'm gonna retain this in mind, that each time I integrate, I'm gonna have a constant, a constant of integration, but keep in mind that I'm gonna pile them up at the end by a new constant, which I'm gonna be labeled like k or c or something, right? All right, so please keep this in mind. I'm not gonna do it as we did it in the first example. I did it once, but keep that model in mind. Instead of doing it over and over, just keep it in mind, and then remember this whole package, I'm gonna call it as c or something over here. All right, so f of x plus a constant is equal to the primitive of f prime of x dx. Correct? But remember, I didn't add the constant because I'm going to add all the constant at the end of the day. All right, and this is what? This is the primitive of x square root of x dx, because this is what f prime is, right? This guy. It's given to us. Okay? And what is that? This is a multiplication here. This is a multiplication here. This is not addition. This is not addition. This is not the same as this. This is not the same as this. I see nowhere this property above, right? I see nowhere this property above. If we had a sum here or a difference, then I can split, yes. But for multiplication, I have no rule. I mean, check all the properties listed above. I have no rule that points this thing out. All right? So I'm gonna erase all of this. This is not the case. That's not the case. I'm gonna do it differently. What is that? Where is x times square root of x? Doesn't it mean x to power 1 times x to power half? Right? Square root of x, isn't it x to power half? And x to power 1 times x to power half, isn't it x to power 1 plus half? Because you are multiplying two exponential expressions with the same base. Don't you keep the base and add the powers? All right, and what's 1 plus half? It's 3 halves. So we get this. All right, so what do we get then? The integrand now, it doesn't look like a product. I know what this means. This is x to power 3 halves dx. Correct? All right, and this is equal to, this is by property 2 now. By property 2 above, it tells me that this is equal to, let me change the color so I can label it. By property Roman 2 above, that guy is equal to x to power n plus 1 divided by n plus 1. Correct? Plus some constant of integration. Some constant of integration. Now, look, if you start here by plus c, remember, if you start here by c, okay, I wrote c. How about k? And this one is gonna come with its own constant here. Let's call it I don't know, k1 plus k1, correct? Forget about the c for a moment. Let's just isolate this c. Take the c away. Okay, so that thing, if you integrate that guy, is gonna come up with its own constant, correct? And then if you subtract this k from this side, if you subtract it from this side, what's gonna happen is gonna show up here as minus k. Make sense? And then since k1 is arbitrary and k is arbitrary, this package is arbitrary constant, because k1 is arbitrary constant and k is an arbitrary constant, so this difference is an arbitrary constant. So I'm taking this whole thing out, right? Okay, I took the plus back. So I took this whole thing out, and since it's arbitrary, I took it as a c, and that c is arbitrary. Does it make sense? So this is out of the way, and just to have a better representation, because these constants they look ugly. So just to keep it neat, we call this sum of constants as just one constant c. Okay, and that thing remains arbitrary. So it's gonna make up for k1 and k, the underlying k and k1, right? All right. So we get this, and then what? If you want to clean up, this is what? This is equal to 3/2 plus 1, isn't it? What's 3/2 plus 1? Isn't it 5/2? 5/2. And this is 5/2. And dividing by 5/2 is the same as multiplying by the reciprocal of 5/2, which is 2/5. Agree with that? Plus c, where c is an arbitrary constant. So far, so good? All right, so what did we do? We solved this differential equation in the following sense. We found all the f that answer this question. We found all the f, so that if you take this f and plug it in here instead of this f, right? And differentiate it. If you differentiate that thing, you're gonna pick up x square root of x. I mean, you can try it. Okay, and this is the most general antiderivative of this function f that does this job, right? Make sense? However, in our context, we have a condition in addition to those, among all of these functions that solve this differential equation, and this is any function that solves it, it's going to look like this, right? For a constant c, for an arbitrary constant c. So among all of these functions that do this job, I want you to choose, this is what the question is, they want us to choose that function that verify this condition. F of 1 must be 2. So they want the function that passes through the function 1 comma 2, right? So they want the function that goes through the point 1 comma 2. So how do we get that? How do we know which function among all of these, right? Among all of these, remember, for each constant you can figure out a function f. They want the special function that does this job. What do you think? So they want us to find the special function so that f of 1 is equal to 2, right? Which one among all of these functions that does this job? Well, what's f of 1 in general? If this is f of x, what's f of 1? It's 2/5 times 1 to power 5/2 plus c, right? Agree with me? F of 1, they want us to be 2. This is what they want. This is what they want. Correct? On the other hand, any function that solves this differential equation, it looks like this. It looks like this. Remember, all of these are this family of functions that solve the differential equation, they all very much the same, but they're shift of one another, right? Vertical shift. So they want the one that verifies f of 1 equals 2. Well, f of 1 for any such function is going to look like 2 over 5 times 1 to power 5 over 2 plus that constant c. So look at this now. Look at this now. They want 2 to be this much. So this becomes an equation that's going to reveal what c is for us. So it's going to tell us which of these primitive functions that's going to do the job. It's going to tell us exactly which c it is, right? But once you reveal c, you know exactly what function we're talking about among all of these functions that belong to that family, right? All right, so that is to say 2 is equal to 2 over 5 times 1 to power 5 halves. What's this? 1 to power 5 halves. This is 1, right? 2 over 5 times 1 is still 2 over 5 plus c. Plus c, right? So can't you solve for c now? How much is c? Well, c is going to be 2 minus 2 over 5, right? 2 minus 2 over 5. And if you do the same denominator here, which is how much? 10? 5. So it's going to be 10 minus 2. 10 minus 2, which is 8 over 5. Agree with me? So that's the c. That's the c that's going to do the job. So long story short, what's the function that answers the question? And the question is, among those which solve the differential equation, among all of these, right, for all c, choose the one that solves also the initial condition. It turns out that the c should be 8 over 5. So it's going to be this guy, where this guy is equal to 8 over 5. So it turns out to be 2 over 5 x to power 5 over 2 plus 8 over 5. Make sense? So that's the function that answers this and this and this. I need both. Make sense? Because I have a whole family that solved this question. But to solve both with this initial condition, I have one and only one, namely this function. All right? So this is as the desired function. Make sense? Excellent. Moving on. Find f if f double prime of x is equal to 12x squared plus 6x minus 4. What is this again? This is an equation that involves the derivatives, in this case the second derivative of f, of a function. So this is a differential equation. So I want to find f such that this happens. Its second derivative is this much. And I have these two verified. What are these guys? F of 0 should be 4 and f of 1 is equal to 4. So these are going to reveal to us the special function that does all three jobs. The differential equation, it solves the differential equation, it solves this initial condition, and solves this initial condition. These are two initial conditions. Why in this case we need two initial conditions as opposed to one as before? Well, where did we use one? Where did we use this one, by the way? We used it to reveal the constant c, correct? How many times did we integrate? Since we differentiated once, we had to integrate just once. So we're gonna pick up one constant. So we need one initial condition. Over here, we're gonna have, we're differentiating twice. So how many times we're gonna integrate? Twice. Right? We're gonna integrate twice. And as such, each time we integrate, we're gonna come up with a constant That's gonna give us one of the two constants, and that's gonna give us the other. I'm just telling you the philosophy of the, of the problem up to this point. No details, correct? All right, so the plan is to integrate this function twice. It's gonna give me two constants. For each integration stages, I'm gonna pick up one constant, and these two initial conditions, they're gonna reveal to me what these constants are. Hope it makes sense. All right, let's do it. So we're gonna go from f double prime to the first one after we integrate. If we integrate this one, what does it mean? We're gonna find a function so that the derivative of this function is this guy. That's f prime of x, correct? Plus a constant, but again, as we said, the constants, we're gonna pile them up at the end of the day. So one more time. If you integrate that thing, you get that thing. Why? Because, look, that's the same as the derivative of f prime. Am I correct? This is the notation of the prime, right? At x dx. Correct? If this function is labeled as g, and if you integrate that thing, what did we used to have? We used to have g of x plus a constant again, but don't worry about the constant because we're gonna pile them up. Do you agree with me? We get this. So who's g for me? Just look, what's g over here? Let's reveal what g is again. This is f prime, you see it? It's f prime. So who's gonna be this guy then? It's f prime. It's right there. This is why we get this. Hope it makes sense. Very good, so let's keep going. We're gonna integrate f double prime one time to get f prime. And this means we're gonna integrate 12x squared plus 6x minus 4 and dx. And the notation is we're integrating the whole thing. We're gonna have the parentheses, right? All right, we're gonna apply the linearity of integration, which means it splits addition and subtraction, and it allows us to push out multiplicative constants. I'm talking about properties 1 and 2 in the theorem above, right? So that's gonna tell me this. I'm gonna use them immediately. This is gonna tell me that this is 12 times the primitive of x squared dx plus 6, that multiplicative constant, times the primitive of x dx minus 4 times, all right, let's just keep 4 inside, minus primitive of 4 dx. If you push out the 4, you're gonna be left with 1 here, right? This is the same thing. Okay. All right, and this is what? This is 12 primitive of x squared. This is by property Roman 2, and the list of properties above. You're gonna add 1, divide by the sum, 2 and 2 plus 1. So you're gonna get x2 plus 1 over 2 plus 1, right? This is by property 2. Plus, similarly, by property 2, you're gonna have, what's the exponent here? That's 1, right? So you're gonna have n plus 1 over n plus 1 minus, what's the primitive of a constant dx? This is property Roman 1 above. Primitive of n dx, that's nx plus a constant. Again, each one is going to bring its own constant, and that one here had a constant because we integrated. We pile them up. How about C for that this combination of constants? So C, keep in mind, C is an arbitrary real number. So where C is an arbitrary real number. Correct? And then let's do this quickly here. What's 2 plus 1? 3. 12 divided by 3 is 4. X to power 3, right? Plus 6 divided by 1 plus 1. What's 1 plus 1? 6 divided by 2? 3. X to power 2 minus 4x plus C. Don't forget, C is an arbitrary real number, right? All right. What is that? This is f prime. This is f prime. Let me write, this is f prime. So f prime of x is this much. Okay. All right. So I got my hands on f prime. This is not what they want. They want the f. All right. But this is something we've dealt with many times above. So how do we pass to f? Integrate one more time. As I promised you, we're going to integrate twice because we are differentiating twice here, right? We're going to integrate twice to undo each time we differentiate it, to get all the way down to the initial function f. All right, let's do it again. F of x, again, plus a constant, is the primitive of f prime of x. We're not writing that this constant here because, again, we're going to pile them up at the end of the day like we used to do here. This is equal to the primitive of 4x cubed plus 3x squared minus 4x plus that constant c dx. What did I do here? I mean, look, f prime is all this polynomial, right? I just replaced what f prime is. Okay. Now we're going to integrate. So we're going to integrate this sum of entities. So it's the same as integrating each summand and then summing the integral up, right? All the integrals. So we're going to have, because 4 is a multiplicative constant, I'm allowed to push it outside. 4 primitive of x cubed plus 3 primitive of x squared dx minus 4 primitive of x dx plus the primitive of c dx, right? C is a constant, don't forget. Okay. All right, so primitive of x cubed dx. This is by property Roman 2 above. That's the same as 4 times x to power 3 plus 1 over 3 plus 1. Am I correct? By property 2 above, plus 3 times, same thing, x to power 2 plus 1 divided by 2 plus 1. For the same reason, property 2, minus 4 times x to power, this is 1 here, right? 1 plus 1 over 1 plus 1 over 1 plus 1 plus, what's going on here? So this is the primitive of a constant. This is property 1, Roman 1 above. Property 1, it tells me primitive of this is cx, and then I'm gonna add the constant. So each one gives me a constant, and this one here, it's constant. All these constants are piled up and calling them, I mean, their sum, their difference, whatever, all the packages refer to as k. Okay, what's k? Again, it's an arbitrary real number. Make sense? So that's the same then as equal as what? 3 plus 1 is 4. 4 divided by 4 is 1. So that's going to be x to power 4. Okay. Plus 3 divided by 3. This is 3 here. 3 divided by 3 is 1. X to power 3. Minus 4 divided by 1 plus 1. 4 divided by 2 is 2. X to power 2 plus the cx plus k. Make sense? So this is f of x. Is this the f of x that we want? Kind of. That's the f of x that solves this problem, that solves the differential equation. This one, right? But this is a whole family of functions. Remember, because c and k are arbitrary. C is arbitrary and k is arbitrary. So this is a whole family of functions. Each one of them for a specific c, for any c, for any k you choose, any function as such is going to solve this differential equation. Now the question is, which one among all these guys that solve this differential equation also verify these two initial conditions, this one and this one? So each one is gonna tell us what the combination of the two is gonna tell us what the constants C and K are. The constants C and K are. Make sense? All right, let's make use of those. Change color here. So I know that f of 0, correct? I know that f of 0 is 4. We want this to happen. Yes? But on the other hand, what's f of 0? F of 0, the function f that's part of this family. Well, f of 0 is going to be 0 to power 4 plus 0 to power 3 minus 2 times 0 to square plus c times 0 plus k. So what's f of 0? F of 0, look, it's this bunch of zeros plus k. So it's k. F of 0 is k. Agree with me? So how much is k then? How much is k then? Is equal to 4, right? So k is equal to 4. So k is equal to 4. Right? So now I know what k is. I know what k is. It should be 4. The other initial condition that we have, is f of 1 is equal to 1. And this is something we want to force, right? We want this. F of 1 is equal to 1. But what's f of 1 for any function f verifying the differential equation? So for any function f that belongs to this family of functions, well, it's going to be 1 to power 4 plus 1 to power 3 minus 2 times 1 squared plus c times 1 plus k, right? So one more time. What's f of 1? F of 1 is 1 to power 4, so 1, plus 1 to power 3, so 1, minus 2 times 1 squared. 1 squared is 1. 2 times 1 is 2 minus 2, plus c times 1, so plus c, plus the k. And how much was k again? We found it. It's 4. Correct? So how much is c then? Solve for c. Solve for c. You have this sum should be 1, right? What's 1 plus 1 minus 2? 0 here, right? 1 plus 1 is 2. 2 minus 2 is 0. So c plus 4 is equal to 1. One more time. 1 plus 1 minus 2 is 0. So this whole thing becomes c plus 4. And it should be equal to 1, you see? It should be 1. So that's exactly what I wrote. And what does it mean? So c is how much? Negative 3, right? So c is negative 3. All right. So now we're done. Now we know exactly what c is and what k is. So among all of these functions f, the special one that verifies not only the differential equation, because I have infinitely many functions verifying this differential equation. Remember, because we have any function with that c with that k, no matter what c and k are, is going to verify this differential equation. But the one that verifies all three together, the differential equation and the two initial conditions, is the function f with c equals minus 3 and k equals 4. So now I'm gonna ready to finally list that function. So all in all, the function that solves the differential equation, allow me to abbreviate here just because I'm using acronym, not abbreviating, just because of the room, I don't have enough room. So solves the differential equation with the initial conditions. How about ICs for initial conditions? Is f of x equals x to power 4 plus x cubed minus 2x squared. I'm copying this, right? Plus c, how much is c? Minus 3. So minus 3x plus the k. How much the k? 4. That's the function that does the job. Okay. All right, let's move on to the next example. So this is a rectilinear motion problem. So remember, if an object has position function s equals f of t, right? If this is the case, if s of t is the motion or the position function of a certain object or a particle, then we know that v of t, the velocity function, is s prime of t, right? Is s prime of t. Correct? So the derivative of the position function is the velocity function. Or in other words, the position function is an antiderivative of the velocity function. Make sense? So because the derivative of s is v, then that's the same thing as saying that the position function is an antiderivative of the velocity function. And likewise, because the acceleration is, as we've seen before, derivative of the function v, which is the derivative of the velocity, then what can we say? We can say the velocity function is an antiderivative of the acceleration. Correct? So v prime is equal to a means v is an antiderivative of the acceleration function, and s prime is equal to v means that the position function is equal to is an antiderivative of the velocity function. Make sense? All right, so let's apply this here. What do we have? We have that a particle is moving in a straight line. So it's a rectilinear motion and has acceleration given by a of t is equal to 6t plus 4. Its initial velocity is v of 0 equals minus 6 centimeter per second. Remember, velocity may be negative, may be positive. It's the speed that has to be the absolute value of velocity, right? So this means that the velocity is, or the object is going in the negative direction at moment 0. And its initial displacement, so its initial position, is at 9 centimeter. The question is, find the position function s of t of that particle. All right. So since acceleration is equal to v prime, the derivative of the velocity function, so the velocity function is an antiderivative of the acceleration. Correct? So the velocity function is an antiderivative of the acceleration. Make sense? I mean, in terms of previous notation, what's a? Isn't a of t, isn't the acceleration function v prime of t? Correct? Isn't a of t v prime of t? The derivative of the velocity isn't it the acceleration? So don't we have this like we previously did? Again, plus the constant here, but don't worry, we're piling them up at the end. Yes? So this is the setup. So I can erase and write that, right? Okay, and this is equal to, primitive of a of t. What's a of t? 6t plus 4 dt, right? And the whole thing is a of t. This whole thing is the integrand. All right, this is not bad. This is equal to, by using the linearity of integration, so we get 6 times the primitive of t dt plus 4 the primitive of dt, right? Okay, I'm using property 2 above. What's the primitive of t? Isn't it t to power 1 plus 1 over 2? So t to power 1 plus 1, so 2 over 1 plus 1. Plus, what's the primitive of this? What's the primitive of this? Isn't it, what's the primitive of 1? This is technically 1. I could have left the 4 inside. What's the primitive of constant dt? Isn't it that constant times t? So we get 1 times t, which is t, plus we're piling up now all the constants. Let's call it c, where c is an arbitrary constant. Okay, and if you clean up a little bit, so vt how much? Vt is 6 divided by 1 plus 1, so 3, because 6 divided by 2 is 3. T to power 2 plus 4 t plus c. Again, c is an arbitrary constant. We said this. All right, now we're down to the velocity. We're gonna move now to because the desired thing is s, the position function. So we still need to integrate one more time because we know that the position function is an antiderivative of the velocity function. We know that s prime is equal to v, right? So what can we say then? We can say that s of t is equal to the primitive of v of t dt. Why again? Same as before. That thing is s prime of t. So we're back to this setup. F of t equals primitive of f prime t dt, right? Makes sense? Okay. So this is then equal to let me change the color again. So this is equal to primitive of vt. What's vt? It's all the sum. 3t squared plus 4t plus c dt. Let's integrate. By now it should be, we should do it quickly. So this is 3t cubed over 3 by property 3, right? Property 2, right? Plus 4t squared over 2. Why? Because this is 1 technically here, right? This is 1 technically. So 1 plus 1 is 2. Divide by 1 plus 1. Plus primitive of c. Primitive of c. What's primitive of c? Is ct, right? Plus another constant of integration k. So where's k and c are arbitrary real numbers. Yes? So probably I did it a little fast, but it's because we've done many problems similar to this before. You split the sum first and then you push out multiplicative constants like we did above or before. So we push the 3 out, we integrate t squared. If you integrate t squared, this is t to power 2 plus 1 over 2 plus 1. And 2 plus 1 divided by 2 plus 1 is t cubed divided by 3. Plus same thing here, you push the 4 outside, t to power 1 plus 1 over 2. 1 plus 1 plus ct plus a constant, right? Okay, and what's 3 over 3 here? So 1. 4 over 2 is 2. T squared plus ct plus k. Again, c and k are arbitrary constants. Make sense? All right. They gave us, however, these two conditions. This and this. Correct? We're going to use them. Guess for what? As you may guess, we're going to figure out what c and k are. Make sense? Let's do that. Let's start by the v to figure out what c is. So we know that v of 0, they told us that v of 0 is how much? They told us that this is equal to a -6 centimeter per second. This is what they want. And how much is v of 0? Well, v of t is this much. What's v of 0? It's 3. This is v of t for any t, right? When t is 0, this is going to be 3 times 0 squared plus 4 times 0, because t is 0, plus c. Now what is that? This is 0 plus c, so this is c. So how much is c at the end? C is simply -6. So now I know what c is. That c that you see here is -6. You might think, oh, it's gonna change the process, but look, -6 is a constant, so it would have behaved the same way, right? If this is -c, you're gonna pick up -ct, right? Nothing is gonna change, it's still a constant. All right, now down to k. They told us that s of 0 is equal to 9. Am I correct? S of 0 is equal to 9. This is what they told us above. What's s of t? S of t is this much, this polynomial. What's s of 0? It's 0 cubed plus 2 times 0 squared plus the c, which is -6, but still times 0, plus k. And what is that? What is that? This is 0 plus k equals 9. So this is k then, which is 9. Alright, let me just erase this and box the equality too. Alright, so c is negative 6 and k is plus 9. So what's s of t? This is what they want, the function s of t, the position function of the object, of the particle. So as a consequence, let me go back to brown, the brown color here. Okay. So what do we have? We have that as a consequence, s of t is equal to t cubed plus 2t squared plus the c, which we found that this is negative 6t, plus the k, which is 9, is the position function of the particle. All right? Okay. All right, the last example, which I'm not going to do, I'm going to just leave it as an exercise for you. Let's read it. A ball is thrown upward with a speed of 48 feet per second from the edge of a cliff, which is 432 feet above the ground. Find the height above the ground t seconds later. So we're going to find the height function and the height above the ground of this ball t units or t seconds later. All right? When does it reach its maximum height and when does it hit the ground? So how are we going to start this thing? Well, an object, if it's near the surface of the Earth, is subject to something called gravitational force. Okay? It's a force based on the gravity. All right? And that's going to produce certainly a downward acceleration. Okay? You see this? It's going to, that's the only force of a free object that's close to the surface of the Earth. Okay? And that downward acceleration the value is approximately 32 feet per second squared, or if you want to deal with meters, it's 9.8 meters per second squared. In this case, we're going to deal with feet because everything is given for us in feet. Okay, and since it's a negative direction, it's a downward direction, I'm supposing that positive direction is upward. That's my positive direction. And since that gravitational force is a downward acceleration, I'm going to have a negative attached to this acceleration, right? That's the only force that's going to operate or that's going to act on this object ball. Make sense? So we're going to start from this. And similarly as before, if you integrate this once, we get the velocity function. And if you integrate this twice, we get the position function. And the position in this case is a height, right? Because we are throwing the ball upward. And the assumption here is it's going to remain vertical, right? It's going to remain vertical all the time. Okay, so no inclination. So the position function in this context is a height. Okay, so the treatment of this problem is very much the same as the one just finished above. And moreover, if you're gonna tell me, oh, I'm gonna integrate twice, right? I'm gonna integrate from a down to the position function twice, as we did in the previous example. So we're gonna pick up two constants. What type of initial conditions we have? Look, they told us that the speed is 48 feet per second. and it's going upward at moment zero, right? At moment zero, the velocity is 48 feet per second, and upward in this context is the positive orientation, because we said that downward is the negative orientation. So this means that the velocity and the speed are the same, because the speed, as you remember, is the absolute value of the velocity. Long story short, this means that v of 0 is 48. V of 0 is 48. So that's going to give us one of the constants of integration we're going to pick up along the way. And the other one is that the ball is thrown at height, from that position of height 432 feet above the ground. So h of 0, if you call the function h to be the height function, the position function, at moment 0, this is equal to 438, right? Because at moment 0, the ball was at this height. Okay? So these two conditions are going to be the initial conditions, and at the end of the day, you're going to have the same problem as before up to this point, right? Up to this point, all these things are exactly the same as before. The treatment of this problem is exactly as before. The previous example, that's what I mean by before. Okay? Now, furthermore, the question here, there are two more questions. When does the ball reach its maximum height? Well, the maximum height means when the function v is 0, right? When the velocity of the ball is 0. When the function position has reached its maximum. Remember, when it reaches the maximum, it means that the derivative function has vanishes. Correct? The function itself, the height function has a horizontal tangent at this point. In this case, the velocity is the derivative of the height function, so this is when the velocity function vanishes. Okay? And finally, when does the ball hit the ground? Well, hitting the ground means the position function at this point is 0, right? So this is equivalent to saying when is the position function equals 0. Make sense? All right, so that's gonna complete this section.